Hi. It's a demonstration of how we might be able to use visualization and human computer interaction for a community to stitch together reality of a real time fire event based on the coupling of imagery data and models. You can watch this video here with the QR code or on YouTube. Just look 2019 Maria Fire or SimTable videos. You can find it, or you can grab it with this QR code. So this was uh, the Maria fire. Started on October 31st, Halloween night, 2019. What you're seeing here is a perimeter taken from an aircraft in the infrared 2 days after the start of the fire. The fire started here at about 6 o'clock at night on Halloween night. And this was really some of the first intel released to the public about where the fire was. On November 1, there was a drone in the area, so the infrared flight was canceled. So what we're showing here is now, can we actually construct this reality? Can the community, in a decentralized way, construct reality together of this fire based on imagery and models? And how can those two be coupled together? And what kind of human-computer interaction can people do as they stitch it together, much like someone pieces together a jigsaw puzzle as a collaborative event. Some people will be working on this side of the fire with some imagery, and other people here, but also interacting with a model that they're trying to fit based on the imagery, and the model also constrains where the images themselves, we have uncertainty of the location and orientation and lens properties. So how can the model actually help us reduce that uncertainty by kind of taking advantage of constraints of how we know fire spreads on the surface and how the smoke plume moves? So as we advance in time here, so imagine now a 911 call comes in and it's reporting a fire up on South Mountain. We're in Ventura. Los Angeles is off to the east, and we got the 126 and the small regional airport. Well, here comes the first camera, and this is an infrastructure camera that's available to the public on alertwildfire.org, and maybe it's about 20 miles away. So the first bit in this visualization is grabbing that camera and locating it. We have some idea of where it is, and bringing it into a visualization that we're now putting the orientation and focal length on that camera. And as this camera gets more and more calibrated, we can more accurately project the pixels in this image onto the landscape or onto the smoke plume. So right now we're going to come in and fly into this camera, and you can see down at the bottom we're at 6 o'clock at night on Halloween night. And here is the start of that fire up on the hill. And we just got the very beginnings of that fire. And 20 miles away, and we only have HD resolution on this camera. A mobile phone, is going to be 5 megapixels, or eight, or sometimes 18 megapixels, compared to a 2K image coming from a web camera in this example. So now what we're going to do is project those pixels onto a digital elevation model, which also has uncertainty, but it's something that helps us tune the camera, because if we can find these peaks, so that model of the elevation can help us figure out our field of view and orientation, so that we can now project this imagery onto the fire. On this demonstration that we did 3 years ago, we're mainly going to be focused on our model that is a surface spread based on kind of Rothermel type of propagation, built in the 70s. But we've it's been advanced with computing and making it more real time and interactive. But at the end of the day, it's still a surface spread model. Modern fire models are starting to look at the plume, the convection, and being able to really model a lot more complexity. And in many cases, wildfires, you can only see the plume in the beginning and can't see the surface anyway. So the next step here is we'll go ahead and project these pixels onto the landscape. And you can see we're far away, so those pixels are very big, but it gives us a rough idea of where this is. Now, here's comes an image on social media. The airspace hasn't been shut down yet, so a private pilot is flying by and holds out their iPhone and takes this picture. Now, the human computer interaction that we want to be able to do is to grab this person's photograph. So if you see, here's their photograph. And if we come back out over here and we show where that, so the first question is, where was that taken from? And we're showing it already solved, but what could the human computer interaction look like where we're finding features in that image and features on this landscape from satellite imagery or aerial imagery we already have. And as we find those correspondence, we can constrain where this camera could possibly be and its field of view and lens distortion properties, right? And its yaw, pitch, and roll. So once we have this, you can see now that we're able to project that image at a higher resolution than our alert wildfire camera, we now have a pretty good sense of the first perimeter in the first minutes of this fire. Now, as we back up to the other camera, we'll pack up here. Now we're starting a model. So this model, we can now augment our view, kind of an augmented reality, in the camera to show underneath that infrared of the heat and the heat there, where do we think the surface spread is? Where do you think that's coming from? Now, this model has a lot of inaccuracies, but it's getting tuned more and more with imagery, and it's also now this is the model and where it is going to inform people to where to point their cameras and look for it. So the next step of this process is in a collaborative way and decentralized social media. Here's an example of the public information officer for Ventura County Fire Department tweeting out, "Here's where the fire is," and what needs to happen is to having a map included in these tweets or on Facebook, so that people can open up their cameras in the browser, and if they do that, we can get at with their permission, their orientation and GPS location, which has error. But you're going to see that happening here now, where maybe a citizen sees that tweet, or they get an alert on their phone with a URL. And so now we'll fly into this camera. And now this camera is going to have a lot of error from the GPS, plus or minus 10 meters. It may have a weird orientation. We may not know the focal length, or certainly if it's on Twitter, we don't all that information stripped out. So what would the human computer interaction look like again to calibrate this, and also with a rough idea of where the model's telling us the fire is? So you can see the interaction of model and imagery as we as citizens are collaboratively trying to co-construct reality, leveraging both the model and the imagery. So now as we fly into this, think of the human computer interaction now and machine vision to say this is the current head of the fire coming downhill. So we got a downslope fire, and if this was a video, we'd have very good plume dynamics, which helps tune. Imagine being able to tune our plume dynamics model based on the video of this as well. So now what we're going to do is paint basically a polyline, a vector on this head of the fire. And that could be another citizen collaboratively doing this. The person that took it may be too busy, right? And now here's an important thing. Those red lines were projected onto the landscape. And the difference between where we think the surface spread is and where we're observing it is a correction factor. So either we're not running downhill fast enough in our fire model, based on our relationship of a backing creeping fire downhill. And one other bit is maybe our local wind velocity vector field is was not blowing downhill fast enough. And the beginning of this fire, we might only have 2 or 3 weather stations giving us wind vectors. So, and then simulation of wind as you come through, as you interpolate sparse sensors, how that wind vector field could be updated perhaps as one of the degrees of freedom of this model to bring it downhill more. So now, so that is the correction factor. Imagine a human-computer interaction to actually drag this edge to match this, or or other types of modalities. So now we'll come into another camera, and this will be looking in the infrared, and this could be a home security camera looking here. And now human computer interaction, someone is drawing on here and saying, oh, this is the time of arrival, and maybe doing this every 20 minutes. So at 10 and 10, 10:30 at night, here it is now, 10:50, and so on. And so now we have these isochrons, or contours of time. This is all the same time of arrival, and in between we can interpolate and say what is the time of arrival for these pixels, as they look at their neighbors of time. What is the rate of spread as we find a local time vector in direction and strength of time. You know, you know. Uh, now, as we come back here, now imagine for every pixel we can look up the fuel type and the slope and aspect, aspect being the direction of the slope. That's something that's a prior with this elevation model that we already have. And the fuels are known coarsely, maybe 40 types of fuels, the Scott-Bergen 40, or the 13 types, the Anderson 13. And let's say we're in the Anderson 13 model. And of those 13 models, let's say we can see 6 of those models in the pixels that we can see. 6 of them are here. And for each fuel type, we have a time on the horizontal axis for each one of these panels. And it's basically a histogram for every point in time. Here's a probability density function, or a histogram of the rate of spread, which is the vertical axis. So time is here, rate of spread by fuel type. And you can see over a couple days, yeah, the fire wasn't in here, this fuel, very much, but you can also see a, a very big increase in these afternoon times when the fire has a lot of activity from the heating of the sun and the temperatures, and the plume will be standing up, as they say. So basically, this is the DNA of the fire that can help tune a model, right? And the next step of this is then, not only tracking fire behavior, but people as well. So imagine you have some of your people where they are GPS, and other people you don't. That's kind of a model. And you now need to try to figure out and label people and then track them and to make sure that they stay safe. And what they might want to know is, maybe we establish a trigger point right here that if the fire gets to this point, you want to notify these people they need to move out of here. Or from a human computer interaction, gesturing with your finger on an iPad up this ridge line to say, to protect this cell tower or this school, we need to put a proposed dozer line up this ridge and communicate that to the dozer operators. If I was a parent and there's a Shriner camp here where kids are at summer camp, and I want to know where my kids are, and if my kid is actually moving down the mountain in a bus, then I know that I can evacuate my position and not worry about going to the school. So hopefully this kind of conveys how we can collaboratively construct reality together based on models and imagery, and what kind of human computer interaction needs to be in the middle of that to construct it together. And that's it. And thank you for your time.